The cylinders shown are oxygen cylinders. Usually, when filled with the gas, all these cylinders contain equal quantities of oxygen. But how can an empty cylinder be filled with exactly the same quantity of oxygen? The ideal gas equation is PV is equal to mu RT, where P is pressure, V is volume, T is temperature, and mu is the number of moles of the gas. R is the gas constant. Hence, if the pressure, volume, and temperature of the oxygen in different cylinders are the same, they must contain the same quantity of gas. Since the volume of all these cylinders is the same at a given constant temperature, if oxygen is filled to a certain pressure, all these cylinders will contain equal quantities of oxygen. If oxygen gas in a cylinder is treated as a system, we can reproduce the system by knowing the values of some of the properties of the gas, such as mass, pressure, volume, and temperature. The set of values of properties of a thermodynamic system, which are used to reproduce the system, is known as thermodynamic state, and the properties are also called variables. The state of the oxygen gas in a cylinder is expressed by providing values of its pressure, volume, and temperature. If the values are P, V, and T, then the state is represented by P, V, T. Now, consider the general case of a gas in a container and let the state of the gas be represented by PVT. If the variables that describe the state PVT have uniform values throughout the system and they do not change with time, the system is said to be in equilibrium state. If A, B, and C are 3 points in the system, and PA, PB, and PC are the pressure of the gas at A, B, and C, and TA, TB, and TC are the temperatures of the gas at A, B, and C respectively, and if the state of the gas PVT is in equilibrium state, then PA is equal to PB is equal to PC is equal to P, and TA is equal to TB is equal to TC is equal to T. Not every state of a system is an equilibrium state. For example, if we suddenly pull the piston up, a vacuum is created above the gas, and the gas in the cylinder starts expanding against the vacuum. This is known as free expansion. During free expansion, the pressure and temperature of the system is not uniform throughout the system, and these values change with time. If P, Q, and R are 3 points in the system. And at these points, the pressures are PP, PQ, and PR. And the temperatures are TP, TQ, and TR. Then, PP is not equal to PQ, not equal to PR, and TP is not equal to TQ, not equal to TR. And these values at any point change with time. Hence, the state of the gas is not in equilibrium state. If the piston is completely removed, after some time, the gas is in mechanical and thermal equilibrium with its surroundings. If the pressure of the system is equal to the external pressure, then the system is said to be in mechanical equilibrium. And if the temperature of the system is equal to the temperature of the surroundings, then the system is said to be in thermal equilibrium with its surroundings. The variables that describe equilibrium state of a thermodynamic system are known as thermodynamic state variables. For example, if the pressure, volume, and temperature of a given quantity of gas in a container is denoted by P1, V1, and T1, then its equilibrium state can be identified by P1, V1, T1, and P1, V1, and T1 are the state variables of this system. During any thermal process, if the equilibrium state of a system is changed, this is described by a change in the values of the state variables. If the gas in the container is compressed, and as a result if the pressure, the volume, and temperature of the gas are changed from P1, V1, T1 to P2, V2 and T2 respectively, then the new equilibrium state is expressed by P2, V2, T2. As the name suggests, state variables of a system depend only on the state of the system and they do not depend on the path through which the system is taken to attain this state. All the variables that describe an equilibrium state of a system may not be independent of each other. If pressure, volume, and temperature of a given sample of gas in a container describe its equilibrium state, then the volume of the gas depends on its pressure and temperature. The relationship between state variables is called an equation of state. For a sample of mu moles of an ideal gas in a container, the ideal gas equation PV is equal to mu RT is the equation of state. From this relation, we can understand that of the three variables, P, V and T, only two are independent, and the third one depends on these independent variables. In the case of real gases, the size of the molecule is not negligible compared to the average separation between them. And the intermolecular attraction is also not negligible. By taking the above two facts into consideration, van der Waals has derived an equation of state for a real gas, which is P plus A by V square, V minus B is equal to mu RT, where A and B are constants. The constant A is related to the average force of attraction between the molecules, and the constant B is related to the total volume of the molecules. The state variables discussed so far are of two types: extensive state variables and intensive state variables. A state variable that depends on the size of the system is called an extensive variable. For example, the volume of a system depends on its size, and hence it is an extensive variable. Mass and internal energy are other examples of extensive variables. On the other hand, an intensive variable does not depend on the size of the system and has a uniform value in different subdivisions of the system. The pressure of the gas and temperature of the gas do not depend on the size of the system, and hence they are intensive variables. If a system of gas in a chamber, that is, in an equilibrium state, is divided into two equal parts, the variables that remain unchanged are intensive, and variables whose values are halved are extensive. We can see that there will be no change in the pressure, density, and temperature of the gas. Hence, pressure, density, and temperature are intensive variables. On the other hand, mass, volume, and internal energy are halved, and hence these are extensive variables. In any thermodynamic equation, quantities on both sides of the equality symbol must be either extensive or intensive. For example, the quantities on both sides of the following equation are extensive. Delta Q is equal to delta U plus P delta V, where delta Q is the heat exchanged, delta U is the change in internal energy, P is the pressure, and delta V is the change in volume of a gaseous system. Here, as delta Q depends on the mass of the system, it is extensive, and though P is intensive, the product P delta V is. Let us first learn about the quasi-static process. Consider a wooden box with two chambers separated by a wooden partition. A sample of a gas is filled in the first chamber, and there is a vacuum in the second chamber. Let the equilibrium state of the gas in the first chamber be expressed as P1, V1, T1. If the partition is suddenly removed, the gas starts expanding freely against the vacuum. During this free expansion, the pressure and temperature of the gas are not uniform throughout. For example, if A, B, and C are three different locations within the box as shown, then the pressure and temperature at A, B and C are different. Since the pressure and temperatures are not uniform throughout the system, the gas in free expansion is in a non-equilibrium state. Eventually, after sufficient time, the gas may settle at a final equilibrium state, P2, V2, T2. If we want to represent the process in a PV graph, we can only represent the initial and final states of the system as I, P1, V1, T1 and F, P2, V2, T2. We cannot identify the intermediate states as they are non-equilibrium states, and hence they do not have a well-defined pressure and temperature. Hence, in thermodynamics, it is always difficult to deal with systems in non-equilibrium states. As a consequence, a quasi-static process, an idealized process in which the system is in an equilibrium state at every stage, is defined. Let us understand what a quasi-static process is. Now, let us imagine that the vacuum chamber of the box we have considered earlier has a large number of similar partitions. We know that the initial state of the system is P1, V1, T1. If the first partition is removed, the gas quickly expands and there will be a small change in the pressure, volume and temperature of the gas. Since the changes are very small, the system quickly attains a new equilibrium state. The new equilibrium state can be represented in a PV graph by point A as shown. If we slowly remove the partitions one after the other, at each stage, the system will quickly be in different equilibrium states. These different equilibrium states can be represented in a PV graph by points B, C, D, etc. When all the remaining partitions are also slowly removed one after the other, the gas passes through different equilibrium states and attains its final equilibrium state P2, V2, T2. The same thing can be graphically represented in a PV diagram as shown. The process we have shown is an idealized process in which the system is in equilibrium state at every stage. Such a process is called a quasi-static process. In principle, a quasi-static process is infinitely slow. As a result, the variables of the system change so slowly that at any intermediate stage, its state is an equilibrium state. This means that at every stage, the system is in thermal and mechanical equilibrium with its surroundings. In practice, a process that is sufficiently slow and with very small differences in the pressure and temperature between the system and its surroundings is a good approximation of an ideal quasi-static process. For example, If we want to take a sample of a gas in a container with a light movable piston, from an initial state P1T1 to a final state P2T2 through a quasi-static process, at every intermediate stage, the gas must be in thermal and mechanical equilibrium with its surroundings. To change the pressure of the gas from P1 to P2 through a quasi-static process, first, the external pressure needs to be changed by a small value, delta P. Then, allow the gas to equalize its pressure with that of the surroundings. Again, change the external pressure by a small value. And again, allow the gas to equalize its pressure with that of its surroundings. Continue the process slowly till the pressure of the system reaches P2. This way, we see that at every stage, the gas is in mechanical equilibrium with its surroundings. In the same way, to change the temperature from T1 to T2 through a quasi-static process, the temperature of the surrounding reservoir must be changed by a small quantity, delta T. By choosing reservoirs of progressively different temperatures, the temperature of each varying by a small quantity delta T, we can take the temperature of the system from T1 to T2. Usually, for our study of thermodynamics, we deal with quasi-static processes only. Now let us discuss isothermal process. If the temperature of a system is maintained constant throughout a thermodynamic process, it is called an isothermal process. A slow expansion or contraction of a gas in a container with dithermic walls is an example of an isothermal process. A dithermic wall is a wall that is capable of conducting heat. To maintain a constant temperature, the gas absorbs heat energy from the surroundings during expansion and releases heat to the surroundings during contraction. Since the internal energy of an ideal gas depends only on the absolute temperature of the gas, there will be no change in the internal energy of an ideal gas in any isothermal process. This means a change in internal energy delta U is equal to 0. Then, for an ideal gas in an isothermal process, the first law of thermodynamics, which is given by delta Q is equal to delta U plus delta W, reduces to delta Q is equal to delta W. In an isothermal process, during expansion, the gas absorbs heat from its surroundings and performs an equal amount of work on the surroundings. Similarly, during compression, work is done on the gas and an equal amount of heat is released into the surroundings. Now, let us find a mathematical expression for the work done by a system in an isothermal process. Consider mu moles of an ideal gas in a container that is at an initial state of P1, V1, T. The equation of state is denoted by the equation PV is equal to mu RT. Assume that the gas is isothermally taken to a final state P2V2T by expanding the gas. At an intermediate state, if the pressure of the gas is P and the change in its volume is delta V, then the work done by the gas during this process delta W is equal to P delta V. Then, the total work done by the gas during the entire process, in which the volume of the gas is changed from V1 to V2 W, is equal to integral V1 to V2 dW, or W is equal to integral V1 to V2 P dV. But P is equal to mu RT by V. Therefore, W is equal to integral V1 to V2 mu RT by V dV, which is equal to mu RT into integral V1 to V2 1 by V dV, which is equal to mu RT ln V2 by V1. Let this be equation 1. This is an expression for the work done by a system in an isothermal process. The PV graph of a system passing through a process at a fixed temperature is called an isotherm. In the graph shown, we have 4 isotherms representing the behavior of a given quantity of an ideal gas at 4 different temperatures. Another important thermodynamic process is the adiabatic process. If a system undergoes a process in which heat is neither extracted from it nor supplied to it, then the process is called an adiabatic process. This means that for an adiabatic process, delta Q is equal to 0. And the first law of thermodynamics reduces to delta U is equal to minus delta W. In an adiabatic process, the internal energy of a system increases if work is done on the system and decreases if work is done by the system. For example, in a 4-stroke engine, the system undergoes an adiabatic compression in a compression stroke. During this process, the work done on the system adiabatically increases its temperature. In a pass stroke, which is an example of adiabatic expansion, work is done by the system adiabatically, and as a result, there is a drop in its temperature. To restrict any exchange of heat with the surroundings, the system must be thermally insulated. This can be achieved if the system is placed in a container made of an insulating material like wood. Sometimes, a system passes through a process so quickly that there is not enough time for heat to be exchanged with the surroundings. Such processes are also called adiabatic processes. In the case of a compression stroke and pass stroke, the processes are adiabatic due to their speed. The PV curve shows an adiabatic process connecting 2 isotherms for an ideal gas. For an ideal gas in an adiabatic process, The pressure-volume relationship is expressed as PV to the power of gamma is a constant. Here, gamma is equal to Cp by Cv, where Cp is the specific heat or molar specific heat of the gas at a constant pressure, and Cv is the specific heat or molar specific heat of the gas at a constant volume. Let us find an expression for the work done by an ideal gas in an adiabatic process that takes it from an initial state P1 V1 T1 to a final state P2 V2 T2. The general expression for the work done is W is equal to integral V1 to V2 P dV. Let this be equation 1. But for an adiabatic process, PV to the power of gamma is a constant. Let the constant be K. This can also be written as P is equal to K divided by V to the power of gamma. Let this be equation 2. Substituting equation 2 in equation 1, we have W is equal to integral V1 to V2 K by V to the power of gamma dV, which is equal to K into V to the power of minus gamma plus 1 by minus gamma plus 1 from V1 to V2, which is equal to 1 by 1 minus gamma into K by V to the power of gamma minus 1 from V1 to V2 equal to 1 by 1 minus gamma into K by V2 to the power of gamma minus 1 minus K by V1 to the power of gamma minus 1. But P1 V1 to the power of gamma is equal to P2 V2 to the power of gamma is equal to K. Therefore, W is equal to 1 by 1 minus gamma into P2 V2 to the power of gamma by V2 to the power of gamma minus 1 minus P1 V1 to the power of gamma by V1 to the power of gamma minus 1, which is equal to P2 V2 minus P1 V1 by 1 minus gamma. Let this be equation 3. This is the expression for the work done by an ideal gas in an adiabatic process. We know that according to the ideal gas equation, P1 V1 is equal to mu R T1 and P2 V2 is equal to mu R T2. On substituting these equations in the above equation, we have W is equal to mu R into T2 minus T1 by 1 minus gamma. Equations 3 and 4 are the mathematical expressions for the work done by a system in an adiabatic process. Let us discuss another thermodynamic process known as isobaric process. If a thermodynamic process takes place at a constant pressure, it is called an isobaric process. Consider a sample of a gas in a container with a movable, frictionless, light piston. Expansion of the gas when heated is an example of an isobaric process. Since the piston is light, at any point in time during the expansion, the pressure of the gas in the container is equal to the atmospheric pressure. In this case, a part of the heat absorbed is used to increase the internal energy of the system and the remaining heat is used to do work. The work done by a system in an isobaric process is W is equal to P delta V, which is equal to P into V2 minus V1. If the system is an ideal gas, then PV is equal to mu RT. Then the work done by an ideal gas in an isobaric process is W is equal to mu R into T2 minus T1. The PV curve for an isobaric process is a straight line parallel to the axis representing the volume of the system. Another important thermodynamic process is an isochoric process. In an isochoric process, the volume of the system remains constant. Heating a gas in a box of fixed volume is an example of an isochoric process. For an isochoric process, delta V is equal to 0. Therefore, the work done by a system in an isothermal process, delta W is equal to P delta V, which is equal to 0. The heat absorbed by the system is completely used to change its internal energy. This means that for an isochoric process, delta Q is equal to delta U. The PV curve for an isochoric process is a straight line parallel to the axis represented by pressure of the system. The adjacent graph shows all the 4 important processes we discussed in a PV diagram. We